Hi, my name is Tobias Roeder. I work for Rohde Schwarz, and today's topic is Forget About It, benchmarking of flow timeout algorithms for RTE hash tables. The user story is quite simple. As a DPDK developer, I want to benchmark different flow timeout algorithms so that I can integrate various use cases such as ipoque or NetFlow probes, load balancers, firewalls, or in the telco space of 4G packet gateway or 5G user plane functions. Essentially, any integration that requires a stateful connection tracking could be applicable. The scope of this lightning talk is to extend the existing RTE hash cuckoo hash table with timeout algorithms. We are using and checking out also LRU, least recently used tables, as a performance reference. However, those do not really apply for most use cases since their timeout behavior is unpredictable. The four candidates we will discuss are timer wheels, skip lists, LRUs, and periodic scanning. Timer wheels were already introduced in 1987 in the SOSP paper. Skip lists and LRUs are by default part of DPDK, and periodic scanning will be implemented in FlowGet. Let's start with the timer wheel. It's a circular array essentially where each slot represents a time interval. Timers will be assigned to each slot based on their expiration time. One improvement here or next generation is the hierarchical timer wheel that implements multiple wheels for certain time granularities. So this could be seconds, minutes, and then hours. On the other hand, skip lists are a more probabilistic data structure using sorted linked lists. So essentially on the base level, we have a fully sorted linked list with all the nodes. And as higher we go, we essentially have a skip list or fast lane that is able to jump over certain nodes for faster search operations. The LRU, least recently used table, is a fixed size table with different integration options. It always comes with some sort of LRU eviction list. In case of DPDK, they implement a bucket-based approach that resolves the most recent versus least recent entries for up to 4 keys per bucket. Periodic scanning is a quite lazy algorithm. It simply scans through the entire hash table in a predefined interval. We improved that operation. Instead of going step by step through the table, we defined a bucket or slice of 1,000 entries. So essentially, if we want to iterate through the entire hash table for 1 million entries, it only takes us 1,000 operations to scan for the expired entries, shown here in red. In order to qualify the performance difference on paper, we can apply the big O notation. So we have constant time complexity for insert, delete, and expiration for the timer wheel. We also have constant complexity for the LRU insert and delete, same for periodic scanning. Periodic scanning has a linear complexity for the expiration process. Skip lists come with a logarithmic complexity for insert, delete, and expiration. So let's now measure these 4 different candidates. Before that, let's define the architecture of FlowGet. The architecture here is a thread local design. We are using the FlowGet library in the base integration of layer 2 forward. And there we conducted single core testing for non-drop rate RFC 2544. For multi-threading in future, you can use the sharding paradigm via, for example, symmetric triplets RSS. Let's zoom in. Before we discuss the hardware, a big shout out to the AMD Telco Lab. Kiseng Song was kind enough to provide this test setup. Thanks again. On the left side, we have an AMD EPYC-powered traffic generator running TRX version 306. On the right-hand side, we have the device under test running DPDK 2311. Both of them were running Ubuntu Server 2204. Let's take a look at the architecture of the APIs. The three most important APIs are Flow Table Create to spin up the instance, so it takes the Flow Table type, either skip list, wheel, smart scanning, or the LRU, and a configuration for that table. Flow Table Process is the most important API. It takes the instance of the flow table and a burst or array of M buffers. It also requires an externally sourced timestamp. Flow Table Destroy gracefully shuts down the instance. Before we measure, we have to define TRX test profiles. So the first profile is the DNS profile. It's a simple query and response. That means we only have 2 packets per flow. That yields a very high insert rate of 50% and likewise 50% lookup rate. However, for a more realistic telco-centric profile, we define the telco top 50. This includes the 50 most used applications plus their corresponding DNS flows. That results into 1800 packets per flow in average, and a very low insert rate and a high lookup rate of 99%. Before we discuss the results, let's share here the configuration. We always measured with 10 million entries per table. We were using hash CRC, and the flow key was 64 bytes. The timeout selection was for the top 50, 30 seconds, and for DNS, much shorter, 5 seconds. Before we zoom into the results, let's run one example use case. So here we are on the actual server. Let's, for example, verify the CPU. And also let's take a look at the binary. So here we see we have standard RTE DPDK dependencies and also one dependency to libflowget compiled on the target. Before I can measure, I will need to start the instance. I do this by providing the standard layer 2 forward config options, plus here an actual table type, which is the scanning approach, lazy scanning, 10 million entries, flow expiration of 5, and a burst size of 64. After waiting for the instance to come up, we can discuss quickly on the left-hand side the TRX options. So here we are using the telco profile at a load factor of 50. And as the first flows and traffic comes in, we can confirm that we are not dropping any packets. And since we've selected a short timeout, we should see very soon first entries deleted by timeout. So this will increase throughout time. And here we are actually using the scanning approach. Awesome. Let's go back to the actual results. For that, I will zoom in. We are using Plotly to visualize all the results. So on the top half, we're going to have the top 50 telco profile for 30-second timeouts. Left side is gigabits per second, right side million packets per second. Here, LRU will always be the winner. So let's discuss the second best, which is the scanning. Scanning at 64 burst size yielded 79.5 gigabits per second. Respective, that translates to 9.9 million packets per second. If we take a look at DNS, LRU is by far the best performer. However, here we notice that the timer wheel and also a burst size of 64 is the winner, and it has 2 gigabits per second, respective almost 3 million packets per second. So let's sum up. The call to action, or do not forget about it. Periodic scanning yields the best results for the telco framework. However, we have some concerns regarding jitter and latency due to the burst eviction. Timer wheel has the best overall performance and precision. So the question is, why not add a timer wheel to the DPDK library? LRU is the best performer, no question. However, it's not really applicable for most use cases. It's more a caching approach. Future topics for benchmarking could be hybrid LRUs with eviction signaling, applying certain Bloom filters like Cuckoo++ research, or hardware-assisted aging, for example, NVIDIA Docker Flow. Thank you so much for tuning in.